Barber towel.
They asked where everyone was going because we were all seniors. So they were some like perfect.
No.
Like, hey. And then Anne's like, stand for
A little bit into next time.
Everyone laughed. Like, it was no hostility.
Okay, now recall what happens in a transformer, a nice application of Faraday's law. I did it all out on the board, showed you the demos last time in class. A little applet, however, kind of aids the cause of understanding at least what the currents here look like. So let's take a look at the following. And I'm going to have to reset this here for us in just a moment. What we have here is a source of alternating current. This is the symbol that is used for a generator. So my primary coil here on the left-hand side, that's plugged into the wall socket. There's resistance associated with it. Then I've got my secondary coil right here on the right-hand side. There's resistance associated with it. It's not hooked up to anything else. That was just my secondary coil. And now, without showing the magnetism here, but just showing the currents, here's then what happens. You end up then with an alternating current being induced in the secondary that's exactly pi radians out of phase with respect to that of the first. So you end up with an induced current in the secondary due to the primary. However, at the very end of class, remember, I mentioned last time that the same thing happens in reverse. The secondary induces an alternating current in the primary. The current in the primary is the same, however, as that of what is originally caused by the generator itself if no damping occurs. So if we assume that there's no resistance there, if we assume that there's no damping of any sort, then it's like the energy just kind of bounces back and forth between the coils. That's how I kind of think of it. I think of it in terms of oscillators. So if we now ignore the generator and assume that no energy loss is occurring in this situation, then what's happening here causes this. What's happening here causes this. So that's the basic idea of how a transformer works if we ignore the damping. Mathematically describing this is complicated, yes. Is this complicated? Absolutely. But mathematically describing this, as long as there's no damping, is actually pretty straightforward. Here's how we go about doing this. Okay, what we do is we just write down Faraday's law for each coil. So, for example, we're talking about the secondary coil. The EMF that is induced in the secondary is just called V sub S here for voltage. That's equal to the number of turns in the secondary multiplied by the changing magnetic flux through the secondary. However, once again, if we ignore damping, the secondary causes the same thing to occur in the primary. So then, therefore, the induced voltage in the primary would be described in the following way. The voltage induced in the primary is equal to the number of turns in the primary. And now, stated without proof, changing magnetic flux through the secondary is the same as the changing magnetic flux through the primary. These two quantities are equal to each other. If they weren't, in a complicated way, it implies that energy is being created in some way. So the changing magnetic flux through the secondary that's caused by the primary is the same thing as the changing magnetic flux through the primary that's caused by the secondary. In other words, one guy's flipping magnetic field, if you will, is just 180 degrees out of phase with the other guy's flipping magnetic field. One changing flux causes one voltage, same changing magnetic flux causes the other voltage. So if these guys are equal to each other, notice that just the respective V over P's are equal to each other. You end up with a simple transformation equation that looks like this. Like so. So this is how we change the voltage from one circuit to another by using a transformer. by adjusting the number of turns associated with the primary and secondary, you can change the voltage to whatever value you wish. So for example, if we decrease the voltage from the primary to the secondary, that's called a step-down transformer. You decrease the voltage by adjusting the number of turns appropriately. If you want to increase the voltage from the primary to the secondary, that is called a step-up transformer. That's once again done by adjusting here the number of turns. So the way that it works out is in a power generating station, you generate a certain amount of energy per second. It's based upon the rotation of your coil of wire and so on. That's measured in terms of kilowatts. And then what you want to do is you want to step up the voltage to a really high value. You transmit the voltage at a really high value through high tension power lines. Those are the really high voltage lines that you see right next to the power generating stations. And then the reason why you do that, and you'll see this in a problem, is because if the voltage is really high, the current is low, and then therefore the P loss, I squared R, from chapter 26, is a small number. And you keep most of the energy when you transmit it over the lines into the grid, out into the city, etc. But then when you get out into the city, it's at a really high voltage. In order for it to be safely used in homes, you then step down the voltage with transformer substations, as they're called. There's a transformer substation on Lincoln Boulevard in Marina Del Rey, right by, I think it is Bali or Fiji or one of those. That corner that's right there, right by the wetlands, when you're coming into the marina area, right on the corner of, I believe it's Fiji and Lincoln Boulevard, there's a transformer substation. It's all bricked off, so you're not going to really notice it unless you look at it, but that's one of the locations where you're stepping down the voltage as you then pass the energy off into buildings around the city. Yes?
Does it get stepped down in multiple phases? Or
Yeah,
just
usually
one
they
exit?
step it down in multiple phases,
Oh,
okay? Because it depends upon how far you want to deliver it, et cetera.
Right.
Yeah, Rachel?
So the D5 sub B, is that the same as the one?
So this is the changing magnetic flux with respect to
So
time.
it's the same as when you put the like lines on top, so
That's
the
right.
lines.
Yeah, so it's how you change the flux through the secondary that induces its voltage, how you change the flux through the primary that induces its voltage. Okay, Cameron?
When you, depending on the number of terms,
Mm-hmm.
we gave us, like, it goes to phases. If you, like, I increase the number of terms, do you lose more energy as it, like?
Yeah, because as you step down the voltage and you're trying to transmit basically the same energy as you're doing all of this, you have to remember that if you step down the voltage, the current increases, and then therefore your P loss is going to be a bigger number. However, really high voltages are obviously very dangerous. So when there's lots of buildings, there's lots of people nearby, they do have to step it down for safety reasons, but you basically try to step it down at the last possible moment. That way you lose the least amount of energy possible. Now in terms of, by the way, the power itself that is being transformed here, take a look at our P delivered equation. Remember that P delivered is I times V. If you're talking about the amount of energy that's being delivered to the secondary due to the primary, the power transformed I times V is just simply equal to I secondary voltage secondary. But then at the same time, remember that it happens in reverse. If you're transferring the energy from the secondary back to the primary, then the power that is transformed is equal to I primary times voltage primary. As long as there is no energy loss, which is what we're assuming here, remember, in all of this. We get the process started with a generator, and we take away the generator, and everything just bounces back and forth, kind of like a simple harmonic oscillator that does forever. These two numbers are equal to each other as long as there is no energy loss. So assuming no energy loss, this is equal to this. So you end up with just two proportions. It's just power equals power, like so, and then V over N equals V over N. You end up with simple expressions to describe this very complicated situation. Let's just take a look at two problems. When it comes to problems, they're just plug and chug. So as difficult as this stuff is, problem-wise, they're easy. Okay, so here's a typical transformer problem. Not only do you have transformers throughout the electrical grid itself, sometimes within individual devices you can have a transformer. So a radio with a transformer is plugged into a wall socket. Okay, coming out of the wall socket is 120 volts. What we want to do is we want to step down the voltage, however, so you can safely operate the radio to a voltage of 9 volts. As you start to read through the problem, it is just a plug and chug problem, easy enough to do. We just have to make sure we get what we want. Okay, now it's important to understand that both coils of wire, primary and secondary, are within the radio itself. However, one of those coils, the primary, that's what's plugged into the wall socket. So the voltage in the primary is what's coming out of the socket. That's 120 volts. Yes, it's the RMS value. That's perfectly fine. And then we step that voltage down to a voltage in the secondary of 9 volts. Okay, then we have some information about the secondary. It has 10 turns, 0.4 amps is passing through it. Basically calculate the stuff that's going on in the primary. Very easy type of problem. Once again, we just have to make sure we get these ones. So just to kind of picture it, it's like, okay, here's the radio itself. And then this portion of the radio right here, the primary, that's what's plugged into the wall socket. So the wall socket is over here somewhere, like so. And then we've got our secondary inside, like this. There's resistance associated with it. Like so, but we're going to ignore the resistor here in this problem. Okay, now we're given that it's plugged into the wall. That's the voltage in the primary. That's 120 volts. We're going to step it down. So the voltage in the secondary is 9 volts. And now, the secondary coil here has 30 turns. That's NS. Like so, oops, NS. It's 30 turns. And then the current that's passing through there, IS. So calculate the current in the primary. That's easy to do because all I'm going to do is set the IVs equal to each other. So therefore, for the primary, we have IV equals now for the secondary, IV. And then we just calculate the current in the primary. It's literally that easy. So mathematically, let's see what we get. Let's see, so 0.4 times 9, and then divided by the voltage in the primary, which was 120. Comes out to be 0.03. Like so. Okay, notice that at a high voltage we want the current to be small because ultimately that means there's less energy loss to the resistance, even though we're not describing that here in this example. Okay, calculate the number of turns. The number of turns is just the other proportion equation. V over N equals V over N. Like so. V over N equals V over N, primary equals secondary. Solve for the number of terms in the primary. So just cross multiply here to solve for the number of terms in the primary. It's going to be this times this. And then divide by this. Like so voltage in the primary, 120. Multiply by number of terms in the secondary, 30. Divided by voltage in the secondary. This comes out to be 100. So the less turns you have in the secondary, that allows you to step down the voltage, in this case from 120 to 9 volts. And then lastly, the power transformed, it's either side of this expression. It doesn't matter which, because we're assuming no energy loss. So P equals ISVS, so good enough. So the current in the secondary was 0.4 times the voltage in the secondary, which was 9, and that's just 3.6 watts. It wouldn't be anything more difficult than this. So as difficult conceptually as the situation is, mathematically it's fairly easy to describe. But you do have to remember the expressions. IV equals IV, and then V over N equals the rho. Now think back to chapter 26, that exam. I gave you that problem involving what happens if you transmit current, or transmit power, excuse me, at varying voltages. How much loss is there going to be? Most of you, it turns out, were actually able to get that problem correct. A couple of you made a minor mistake. I'm just going to briefly revisit that. Rachel, you had a hand up a moment ago before I go further.
Are the proportions going to be on the sheet?
Honestly, I forget. I'd have to double check, but the equations themselves are very easy. So IV equals IV, then V over anything. They're easy enough. Okay, so let's briefly here revisit that problem. Okay, this problem right here, technically speaking, is a transformer problem, but we're not going to use the transformer equations for the example. That wasn't necessary when I gave this to you as an exam question. Specify it. Okay, let's kind of think of this as a series of stages. So this is the exact same problem as that exam problem. Same number, same wording, whole nine yards. When we approached this problem, it was just essentially manipulating P equals IV and P equals I squared R and just realizing which was which. Okay, but now here's what happens. First of all, we've got the generator. Okay, the generator, remember, is going to generate a peak voltage, epsilon naught, we called it, if you remember last time in class. Okay, what women's sports league was epsilon naught? Yeah, basketball omega, women's basketball. Remember this? So, for the RMS then, is equal to that value divided by 2. Okay, this is controlled by how quickly you rotate your coil of wire, what the area of your coil is, what the magnetic field is that you're using, the number of windings, and so on. So then, therefore, what determines the current that you initially generate? Well, taking this and just setting it equal to, from Ohm's law, I times R. So the amount of current that you start with is basically just this within the generator itself. Okay, now, how quickly you rotate the coil of wire, how much energy you need per second to do this, that's what determines the 120 kilowatts. So the P here that we're starting with in this problem, and this is what's going to be delivered, it's 120 kilowatts, that's 120,000 watts.
How do you know what's being delivered? Sorry.
Okay, so that's the amount of energy per second that's necessary to rotate the wire, to rotate the coil. So therefore, in other words, how much energy per second you put into this, that is then going to determine how much energy you're going to get out of it, which you then transmit across the city. So that's going to be the P delivered. It's determined by how quickly you rotate. So how much energy per second you need to rotate it, that determines what goes on in the generator. So this is a representation of essentially the work you're doing per second in rotating this thing. How much current you actually generate in the generator itself is determined by all of this stuff here. But then what you want to do is you want to deliver this energy per second here at the highest possible voltage. So regardless of what this number happens to be within the generator itself, you want to step it up. You want to step it up to a really high voltage. In this case, let's do part B first, 240,000 or 24,000 volts. So we want to step this up. So it's like the next part of the process, if you will, is a step-up transformer. Such that the voltage now, in part B, we'll do that first, as I said, is 24,000 volts. So then how much current is then actually flowing through the wires when you do this? Well, now we set the P delivered of 120 kilowatts equal to I times V. Now P delivered equals I times V. Find the I. P delivered over V. This is going to be a really small number because the V is so big. It's basically 120,000 divided by 24,000. 120 over 24, and that's about 5 amps. So, and then we've got, the transmission lines, like so. These guys here have a resistance of 0.4 ohms. And then after that, we step down the voltage over here into the buildings, into your streets, etc., etc. And then it all loops back to connect to the other side of the generator itself. Okay, now the P loss, this is where people made a mistake. The P loss is not the V squared over R. The P loss is I squared times R, because this voltage V right here is not the voltage across the lines. This is basically the voltage within the step-up transformer, and then we transmit across the lines. So the P loss here we have to write as I squared R. Those of you that did make an error here in this problem, that's the error that you made. You wrote your P loss as V squared over R as opposed to I squared R. So now it's just 5 squared, which is 25. Square that, 25 times 0.4, and this comes out to only be 10 watts. Now I wrote out the problem as an efficiency calculation, essentially, but notice how efficient this is. We're generating 120,000 watts, and we only lose 10 watts of it in transmitting at a really high voltage. Watch what happens to this number, however, if you transmit instead at a really low voltage, which is part A of the problem. So in part A of the problem, now we just set the V equal to 240 volts, and then once again we use P delivered equals IV to calculate our I. In this case, the I is going to be gigantic. So it's going to be 120,000 divided by only 240. 120, 123 over 240. This is 500 amps. So this will probably fully melt the wires before the current even gets to the city, to be perfectly honest. And then the P loss in this case is going to be absolutely huge. So take 500 and square that, and multiply it by 0.4. This is 100,000 watts. So if you're only generating, by rotating your generator, 120,000 watts, you use 100,000 watts of it, obviously that's not very efficient. The efficiency on the top board for part B is more than 99% efficient. This guy here ends up being something like 16% efficient or something like that, for those of you that went through the remainder of the calculation as we stated on the example. So that's why we have to use transformers. You can't generate a huge voltage to begin with. You just determine how much energy you put into your generator per time to get the P delivered. You step up the voltage into a huge number, transmit the energy through low resistance lines, and then step it down repeatedly when you get to the other side. That's the basic idea of the concept. Somebody had a hand. Yes, Rachel?
Sorry.
It's all right.
Can you just go over one more time? Why do you know that it's I squared R, not V squared R?
Okay, so because the V of 24,000, that's occurring within the transformer. The transformer itself, and the next time, by the way, that you drive by a power generating station, you'll see next to the smokestacks and blah, 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 you'll see a bunch of coils where wires are coming out of these big gray things. Those are the step-up transformers. And then if you look, those gray things are connected to transmission lines, which then go away from the generating station. So the voltage of 24,000 volts, that's within this. It's not from here to here across the transmission lines themselves. So that was an error that some people made. They wrote the P loss as V squared over R, as opposed to what it has to be here, which is I squared times R. But that was what was happening now in detail in that example. Okay. All right, good. Okay, that's Transformers. More than meets the eye.
Wow.
Those movies are really bad. Finally, our last major topic, inductance. Dun, 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 dun. Yes. Did you guys enjoy the trip to Magic Mountain? I love it. Absolutely. How many of you rode full throttle? It's a great ride for the front seat, by the way. How many of you rode Superman? Good. How many of you have ridden the roller coaster at DCA? You guys know what DCA stands for?
Railgun.
Disney's California Adventure. How many of you have been on that roller coaster? All three of those coasters begin exactly the same way. They use an electromagnetic railgun. Let's go through the electromagnetic railgun now here in some data. It goes like this. Now, the first of these two problems that I'm going to show here to introduce this last topic, called inductance, is actually a Chapter 27 problem. You may have seen it in your course of studying Chapter 27. I may have had it as a website for that matter, frankly, I don't remember. But it basically goes like this. See diagram. Right off the diagram. So this is Chapter 27 problem. I could have done this problem in Chapter 27. Frankly, however, I held it off to here for the reason. You'll see. Where's the what? Diagram. So the diagram I'll draw on the The diagram is always on the board. All right, so here's the track on Superman. So, okay, where's the car? The car, we'll just say, rod, like so. A conducting rod that can slide on the track, like so. And then what we'll do is we'll send a current through it in some manner. So over here we'll say, just for now, is a DC current source. So I'll go ahead and put a potential. So then therefore, I'm going to have a current. Let's see, I'm going to flow it into my diagram here like this. Okay, now, if we use F equals IL cross B, where right here we'll say is a distance L. And just for simplicity, this right here, remember, is the car. In order to get a force to be exerted on that rail, which can slide to the right-hand side, we want the force to be like this. In which direction in this region here do I have to have a magnetic field? So I want to have IL cross B, where the IL is like this. I want to cross the B field like so into the board to give me a force in that direction. So you have to have, in an electromagnetic railgun, you have to have present a permanent magnet. In this case, the magnetic field will point into the page. So you have IL through the rail, the car, cross B, like so, gives me a force in that direction. Rachel, did you get your question answered, or?
Are we looking at it from the side or from above?
No, we're looking at it from above.
Okay.
So you're on top looking down on the track like that.
Okay.
So everybody is sitting in the car, that's the rail. And then we pass a current through the car. Are you sitting on a conductor when you're in the ride? Absolutely. You're sitting on insulators though, don't worry, you're not in any danger of getting shot. So you have IL like so, cross B. So there has to be a permanent magnetic field here present like so that goes into the board. Okay, now the next time that you ride one of these rides, look either off to the sides of the track or actually down the middle of the track. You'll see, in the case of Superman, these really huge, what appear to be white boxes. What are those white boxes? Those are the permanent magnets that are supplying the magnetic field, the red vector B. So now, we end up with a force here. It's just equal to ILB. We'll assume a right angle here between I and B. And this is then therefore equal to mass times acceleration. So ILB is equal to MA. However, there's a problem here. Not only is there perhaps a little bit of friction that opposes the motion, of course, in this direction. Remember the basics of chapter 5, the good old days? Friction opposes the motion of the object. Yeah. In addition to perhaps the friction that may point in this direction, there's a problem associated with this. Because right here is an area. Do we have right here this instant of magnetic flux through that area?
Yes.
Yeah, we do. If I take my rail gun, the car, and accelerate it in this direction, what happens to this area? It gets bigger. So you have a changing magnetic flux. Therefore, do you induce a current in the rail gun? Yes, and it points in the opposite direction of what I described here. There's a problem associated with the rail gun. There's a problem with the rail gun.
Maybe it's a challenge.
Yeah.
So like you're referring to like how last time we were talking about the generator radio was more going into the push out.
Okay, so now, yeah, exactly. So if the car accelerates in this direction by just doing IL cross B, chapter 27, okay, no Faraday's law yet, no nothing. This is the force exerted on a current carrying wire due to a magnetic field. The magnetic field in this case is supplied by permanent magnets. So then therefore, if we did this problem back in chapter 27, it's literally nothing more than this. ILB is then therefore equal to MA, and your car accelerates in this direction. But when you do this, now in chapter 29, we create right here a changing magnetic flux, which will then induce what is called a counter EMF. This is referred to as an example of what is called inductance. Now, just to keep this easy to picture, let's say that no current is flowing in this thing, and all that I do is I manually pull the wire in this direction. Let's just look at it like that, just so we can try to dispel as much confusion as possible.
So Sean, question.
Yeah.
So that first equation is just ignoring some.
That's ignoring Faraday's law.
Okay.
This is just chapter 27.
Got it.
The force on a current carrying wire due to a magnetic field. F equals IL cross B, and that's it. So this is what accelerates the railgun. This is what happens when you're sitting on the Superman ride. But there is a problem associated with that, and you can start to think of it in the following way. Why can't you just continually keep on accelerating the railgun? The reason why you can't do that is because of what is called a counter EMF. The counter EMF works in the following way. Okay, so now, as it says in the problem, assume no current flows. And now we just manually pull the car. Now I'll just think of it like this. Like so. And then right here is some distance. Let's give this distance here a name. Let's just call this A. And then right here is then therefore an area. Capital A, which is equal to base times height, it's equal to A times L. Now, I've got my magnetic field. This magnetic field here, like it was in the top board, that's supplied by permanent magnets. It's like I've got a bar magnet nearby. Okay, and then I come along and I manually reach in. And I just grab a hold of the car, and I pull it in this direction. So a few moments later, in other words, my diagram would basically just look like this. Like so. Notice that I drew here more magnetic field lines into the board than I had previously because I've increased the area. The area is changing with respect to time here in this problem as the car is accelerated to the right-hand side. So I now have a changing magnetic flux through this area. If I have a changing magnetic flux through this area, in other words, I'm getting more red arrows into the board, how then must the current flow, the induced current in this case, through this rectangular wire loop to oppose that? It has to go counterclockwise to give me its own magnetic field out of the board. So you end up with an induced current. It flows like this to oppose the changing magnetic flux. So it would be described in the following way. We would have our phi, which is just equal to B times A here to keep the geometry simple. We're now going to have our area here change with respect to time. So d phi dt, that changing magnetic flux would be an A that's changing with respect to time multiplied by B. Depending upon how a problem is stated mathematically in WebAssign, for example, etc., on the AP exam, we would have to describe how that area changes with respect to time in terms of the quantities here. It depends upon the speed of the car at any instant in time. Let's say that the car is moving in this direction with some motion here, as I wrote, with a speed v. You can then describe how this guy here changes with respect to time as speed multiplied by time to get a distance, and then multiplied here by the distance L. So sometimes you'll see this here written out in the following way. Like so. Think of what I put there in parentheses as the changing area. It's basically a distance here, Vt, multiplied then by L. You differentiate that with respect to time. When you differentiate it with respect to time, you just end up with B times L times V. You'll typically see this in basic examples. So that's kind of how the math here begins to play out. But what's most important to realize here is that you get an induced current, like so, to oppose the changing magnetic flux. Now notice the direction of that induced current. Compare it to the original direction of the current that I started this process with up on the top board. Notice it's in the opposite direction. So by literally taking the car and having it move in this direction, it's almost like another battery appears, if you will. There's a counter EMF that always opposes this battery that we started the process with. So it then, therefore, becomes harder and harder for you to keep pushing the car to the right-hand side here in this problem because of the counter EMF that is being set up as you continuously change the magnetic flux. This is why eventually the car will only be able to reach a top speed, because of this additional battery, if you will, this counter EMF, as it's called, that gets induced in the circuit itself. This is referred to overall as a property of what is called inductance. So you can only reach a top speed here with the ride Superman, for example, not just based upon the length of the track itself and how many magnets you have, but also because of the changing magnetic flux induces a counter EMF. So that's kind of like the basics of what's going on in electromagnetic railroad. You can get the process started, but you can't keep it going infinitely because of the counter EMF that builds up. Yeah.
So it's like a counter current.
Yeah, it's like a counter. The way I picture it is just like another battery like appears in the circuit that opposes your original battery. Okay, that's the way that I picture it. That current that's induced, by the way, is always going to be less than this current here. If it was greater, what would that imply about the energy necessary to supply that current? If it was creating something, it would violate conservation of energy. So you can keep on accelerating it, but you're going to have a smaller and smaller acceleration. Hunter?
The Superman geometry, the area isn't two-dimensional. It goes, slopes up.
But next time you ride the ride, you're only going to see the white boxes, the permanent mags. I believe in that particular ride, by the way, they appear as these large bricks that are lined up against the track. It's only for like the first 100 meters or so, and then after that it cuts off. So that's when they get the acceleration as fast as they possibly can, and then blah, blah, blah. And then you do the whole process in reverse when slowing down. It's a little bit easier to see if you just accelerate it from rest as opposed to slowing it down, but it's also the same situation. It causes the brakes to occur. It's basically an electromagnetic railgun in reverse. Somebody else can hammer and then
So you're saying like each time you pass through each permanent magnet, the EMF, or sorry,
Okay, so each time you pass by a permanent magnet, it's like giving us more and more B field. So basically we're trying to make this as big as we possibly can up on the top. You're getting more and more B field, make this bigger and bigger and bigger as best as you can.
Yeah.
However, there's a problem, as this problem here shows. The more B you have here appearing in this area, the more and more you get a counter EMF induced to produce a current that opposes. So if you just have a current that opposes, watch what happens with forces now. It's like through here, the counter EMF is like that, through the car. So now it's IL cross B like so, it's a force in the opposite direction of what is going on over there on the top floor. So in addition to friction kind of acting against you, which you always have anyway, you have this counter EMF acting against you. Eventually you end up with an acceleration of 0, and then therefore you reach your top speed.
So then, all these rides, are you just always going as, are you trying to get as close to having the induced current be?
You're trying to get as close as you can. You're trying to get as much distance out of this as you possibly can before acceleration goes down to 0. Basically.
Yeah, so
Daniel?
Can you explain how you know that the field is
Okay, so if I put, here, I gotta face my hand right. Okay, so through the car, I put the current like that. So then therefore, if the B field is into the board, IL cross B gives me a force that way. So that's why I positioned things the way I did up on the top board. So that B field pointing into the page accelerates the car in that direction. But as we do accelerate the car in this direction, this counter EMF builds up. Okay?
So if the current had gone opposite direction, then the B field would be up.
Then I would have had to reverse the B field. So it just kind of depends upon how you draw it.
Okay.
So I had to make sure I got that right. Okay? Now let's take a short break.
How many did 140. Let me know when you saw it.
Yes.
Oh, I flew out of it, dude. I got every question. I should have studied. Where is
Okay, yeah, so like, when you're
There's a bunch of bricks.
It's not gonna help. Yeah, it's not gonna help. Oh my god, look at your eyes. Look, I learned how to. I'm not pointing so you guys
The problem with this so it could be done at the move like because you can only build such a thing.
It's like do you know what and then she came in my gut, but I'm just.
Yeah, so I just like.
Might as well. Yeah, you do. Okay, so the reason why you don't get struck by lightning is because lightning current will take the damage. So compared to
You
that,
can never make it big.
because you have less resistance. It's the
I'm
amperage.
gonna get an A. I'm really elected. I'm going to take flight on
What it does is
You know what? Two questions. Now I have information. I watched it.
because your nerves are like, there's a potential difference between your brain and you want to make that current small. It's like imagine like as I'm saying, you're trying to pull it in this direction.
I don't know what's happening.
You're looking down on the
Sorry for the
sitting in the car and
Why is that?
because of how I work.
You don't really lay down.
No, I tend to
That's only you after. Your all's gonna show it after.
Broad and out the wire.
Actually, just wants to say with us.
I showed you what
No other after.
So basically, the current goes
Unless you
so it goes through the whole the L crosses B.
I think it's for what?
So let's say you I current that goes the opposite direction. Then you have a running out of the the same effect.
You committed to that school because everything in the group chat told me.
It was a good idea, but I don't think it's a good idea.
Where's the hammer?
Have you sent your bill yet? When do you get asked?
I don't care. I mean, it's very easy.
You mean SIO?
Oh yeah, I know. No, you have to do that when you submit it. I'm pretty sure.
That's like a red exclamation point. Like everything in
You do a long one? 45 tools? Maybe more?
Did you guys?
Yo, join it before cycle.
34 pages of notes.
All right, take a seat, please.
Yeah, you open them all like 4 pages long. I think this is so irritating.
Y'all look we got like a really big house.
It looks like 5 minutes. Legit 3 minutes away from it.
Like right here?
No. You live close to
Are you really rich?
What we take away from the last example is that if you pass a current through a circuit, if you pass a current through a loop of wire, this then creates a changing, and if you change something, this will then create a changing magnetic flux through the wire itself, creating what is called a counter EMF. This can happen with just a single coil of wire all by itself, such as a solenoid, resulting in a property that's referred to as self-inductance. This is pretty tricky. Here's how it works. Let's say that I've got a solenoid. Like so. Let's say I hook it up to a DC source. Let's say that a current begins to flow. Okay, now when the current flows, it doesn't reach its maximum value instantaneously. It goes from a value of 0, eventually reaching its maximum value over a short interval of time. So this then means that for that short interval of time, the amount of current that is flowing through the solenoid is not a constant. It's increasing, it's steadily increasing, if you will. Increasing to its steady state, as it's referred to as eventually. But suffice it to say, it changes with respect to time. Okay, now, just this single loop right here, from Biot-Savart, when a current is flowing, creates its own magnetic field. So just look at the first loop of my solenoid. The first loop of my solenoid is going to create its own B field, which will roughly begin to look something like this. However, as the current changes, eventually reaching its steady state, the magnetic field is changing in magnitude. The lines are tightening up, if you will, as the current increases. So then, therefore, what could you say about the magnetic flux through the coil of wire as a whole? It's changing. It's not a constant. So the B for the current that flows is not a constant. It goes from 0 initially, and it doesn't magically, instantaneously reach its maximum value. There's a period of time while the current goes from 0, eventually reaching its steady state. When this happens, the magnetic field changes. That then means that you have a changing magnetic flux within the solenoid itself. This then creates a counter EMF. So this guy here steadily changes. Therefore, there's a changing magnetic flux through the solenoid. Counter EMF. It's like another battery appears within the solenoid to kind of push back, if you will, against this current that's increasing. Counter EMF appears in the solenoid to oppose changing magnetic flux. This is, yes, admittedly, very difficult to picture. But here's essentially what it looks like if we use, once again, a little applet here to help us out. Okay, so what I have right here in this applet, I'm going to have to reset it for us in just a moment, is a potential difference right over here on the left-hand side, and then right over here is our solenoid. Our solenoid, by the way, is referred to in this context as an inductor. And then right here, these little dots that we see here, this is going to be a representation of the current. Okay, I'm going to go ahead and reset this. And set it. Oops, I'm going to have to refresh it. Let me just, yeah, like so. Notice what happened. Notice that the current started off at 0, and then it kind of like steadily reached its current value like so. Watch it again. Reset it. Like so. It doesn't instantaneously go from 0 to its maximum value. There's a little bit of buildup right here. This yellow graph, which we'll get to later, but this yellow graph right here is describing the current that is passing through this circuit as a function of time. Notice right now that it's a constant once the steady state, as it's called, has been reached. Watch it again if I reset. Like so. And now if I stop it here for just a moment, this green graph right here, that's describing the voltage across the inductor. It's describing the counter EMF. notice that the counter EMF starts off as very large and then drops off. Eventually the current reaches its steady state. When the current does eventually reach its steady state, does the magnetic flux through the solenoid change? If the current is a constant, does the flux change? No. So the counter EMF goes away. In other words, the counter EMF is there at a big number eventually. It's like we start the current flowing and all of a sudden it's like the coil starts pushing back against us. However, once we reach the steady state, then that pushback, if you will, appears to disappear. And that's what you're seeing here in this problem. So once again, I'll kind of reset it. Myself. And then it reaches its steady state. The counter EMF here in green eventually drops down to 0 as the current here approached and then eventually reached its steady state. Describing these graphs, by the way, mathematically is actually really easy. The tough part of all of this is this conceptualizing what has to happen. Okay, now how do we begin to describe all of this? We describe it in the following way. At any instant in time, the amount of flux that is passing through the solenoid, the number of turns of the solenoid multiplied by the flux through one turn, the amount of flux passing through the entire solenoid is proportional to the current I that is passing through the solenoid at any instant. Proportionality is a property of the wire itself. It's analogous to capacitance. It is called, in the magnetic sense, self-inductance. We refer to self-inductance as the letter capital L. Capital L is our last major quantity here for the curriculum. Capital L is called the self-inductance.
The last lecture.
It's analogous to capacitance. Because it's analogous to capacitance, like capacitance, it's basically geometry. It's a property of the geometry of the wire itself. Remember, the capacitance had to do with the area of the plates, the separation between the plates, blah, blah. This is essentially the magnetic equivalent. How much counter EMF builds up in a wire depends upon how you shape the wire. This property is this quantity here referred to as inductance. Now, it is in quantity, obviously, for us. Here are the basic units for it. The metric SI units of capital L is called the Henry. It is named after Joseph Henry, who is one of the principal people involved in the late 19th century in the development of radio communications. It's referred to as the Henry. It's spelled Henry. That was his last name. The plural is Henry's, as I wrote it, not Henries, because Henry is somebody's name. So we write it as Henry's, like that. Okay, now how do you then actually describe the counter EMF itself? Here's then where Faraday's law comes in. In order to come up with Faraday's law, basically what we do here is just differentiate this with respect to time. Because remember that the derivative of flux with respect to time gives us the induced EMF. So just differentiate both sides of this expression to now get an expression for the counter EMF. The counter EMF is equal to the following. ddt n phi sub b, negative for the opposite direction. But n phi sub b is now L times I. It looks like this. So here's how I kind of pictured this. It's like a little battery. If you change the current as we're doing when we first switch things on as a function of time, then it's like a little battery builds up in the coil of wire to oppose the battery that you start the process with. That's how I think of this expression. However, what happens to this expression, the di/dt portion of it, that is, what happens to that number as time goes on and you get closer and closer to the steady state? That is, does this change or does it stay the same? Does it increase? Does it decrease? What?
Decrease.
It decreases. I mean, just think about what you saw. Okay, watch it again. Reset. Starts off, the di/dt is a really big number, and then all of a sudden it slows down and eventually approaches 0. So as time goes on, this number here is getting smaller and smaller. Therefore, the counter EMF gets smaller and smaller. And eventually, the green graph there, which is the counter EMF, it goes to 0. Okay, now watch what happens if I turn everything off. If I turn everything off, what I'm going to do here is take this switch and flick it to the other side. Oops, damn, I didn't do that right. Let me try it again. No. Refresh it, screw you. Okay, so build up to the steady state current. So, and now do this carefully, Dave. There we go. Like so. Notice how it then also went back down to 0. So what happened there? Well, once the steady state current got reached and I flicked the battery away, then this number, once again, begins to go down. And then that battery, if you will, the counter EMF, just think of the coil of wire as a battery that points in this description like that. It pushed the current in that direction through the right-hand side of the loop. The amount of current flowing on the right-hand side of the loop eventually went down. That's what's being described right here. This was the counter EMF when I switched the switch to the right-hand side. That counter EMF eventually went back down to 0, and the current that was flowing eventually went back down to 0. So the easiest way to think of it is to think of it as a battery that always opposes what's happening. So then therefore, if we first of all switch it on, it's a battery that acts in the opposite direction of how the current initially flows. But then when we switch everything off, that results in a change in this. So then therefore, it's a battery that kind of like tries to keep it all flowing again, and then eventually goes down to 0. So this allows us to actually then store energy. It allows us to store energy in a coiled wire, not as a capacitor, which allows us to store energy in terms of electric charge, but instead it allows us to store energy in terms of magnetism. So what you're about to see here is essentially a repeat, if you will, of some of the stuff we saw with capacitance, but now in its magnetic sense. The first thing we do is just learn how to calculate this guy right here, the inductance for just 2 situations. A solenoid and then the coax. Those are the only 2 situations we have to worry about. Is this tough? Absolutely. They save the best for last in electricity and magnetism. Conceptually, the hardest stuff comes right here at the end.
The second part we're trying to
Try to keep the current going.
where you store the magnetic field, doesn't have to be a moving magnetic field, it just afterwards, it's a normal magnetic field.
Okay, so the way that it works is that you switch the current on and you build up this battery, okay? But that counter EMF eventually goes down to 0 when the current flows at a constant rate. The reason why is when the current does flow at a constant rate, there's no changing magnetic flux. However, let's say you switch things off. I just turn off the battery, and the current is still flowing and it now begins to decrease. So then therefore I have a changing magnetic flux, which will create a counter EMF which will seek to oppose that. It will try to keep the current flowing. That's the easiest way to think of it. Is this tough? Yeah, absolutely. One of the old things is supposed to be in the 19th century without electricity and magnetism. Yeah. It makes our lives easy. We waste time on our phones. If we didn't know all this stuff, we wouldn't be able to waste time on our phones. That's entirely what this is all about. I should call this class wasting time on your phones. Here's what I should call it. How are we able to waste time on our phones? That's a good way of stating it. I'll get so many people signing up for the class, they go, oh, we just sit there and waste time on our phones. No, no, no.
You gotta learn how you do it.
You lose a lot of students after.
That's okay. That's all
You
right.
had the highest drop rate of college. 95% drop rate.
The presentation would be so funny.
This is my doodle jump version.
Okay, so we're going to calculate this property called self-inductance of the ideal solenoid. The ideal solenoid is connected up to a DC potential difference, and then eventually calculate the potential energy stored in the solenoid, the energy density of the magnetic field after the steady state current has been achieved. This is kind of like the magnetic version of capacitance with parallel plate capacitor. It's the easiest way to think of exactly what it is that we're doing here. Okay, now just kind of picture the problem the following way. We've got a potential difference like so, and now we've got our solenoid. That's this symbol here. This symbol in circuits is the inductor symbol. Okay, now when the current here first begins to flow, then kind of think of it this way. The counter EMF kind of acts like a battery that pushes in that direction. This is how the counter EMF is going to look here in this problem. How do we add things up using loop rule and so on and so forth? That's the last thing that we have to do. But that's what we do next time. For now, we're just looking at the coil itself. Now, to calculate this property called self-inductance, it's really just one thing. We just have to do this. N phi sub B equals L times I. What we're after here is the L. In order to get the L, we need this. Now, the phi sub B, this is the easy part, because this is just B times A. Remember what the ideal solenoid's magnetic field looks like. We looked at this guy here in detail, just kind of off to the side. Remember that this guy's magnetic field is confined to the tunnel, and it just points in this direction. Okay, the geometry here is always kept as simple as possible. The area vector associated with each individual loop is just in this direction. So the magnetic flux integral B dot dA is just B times A. It always will be and nothing else. It's just B times A. Easy enough, where A is the cross-sectional area of our tunnel. So right here is my solenoid. Right here's the area A, and then the B field just points in that direction. That's it. That's what the flux is. Okay, now, it's been a while, but does anybody remember what the magnetic field B was for the ideal solenoid? Q naught times good. Times I. Yeah, very good, like so. N, if you remember, was the number of turns per length. Like so. Little n was the number of turns per length. B was mu naught Ni. So therefore, the flux is mu naught Ni times A. And we will write little n here, however, as number of turns per length. So, and now we just stick that into here and solve for L. That's all that we do. So we stick it in here. So it's this times another n. So you get an n squared. You gotta be a little bit careful when you do this. Equals times I. So you notice that the current I cancels out. So then therefore, the self-inductance of the solenoid is the following little expression. Mu naught n squared A It's basically just fundamental constant in geometry. The geometry of the solenoid itself. This guy right here is basically the magnetic equivalent of this. Remember the capacitance of the parallel plate capacitor? It depends upon the area of the plates themselves and how far apart they are from each other. This is the magnetic equivalent of it. If you also remember, how well a capacitor stores energy depends upon the capacitance. How well an inductor stores energy, that counter EMF, how well the inductor stores energy depends upon geometry. It depends upon the self-inductance of the solenoid itself. So finding this is easy to do. It's just N phi equals L times I. We already know phi from a previous calculation. Plug it in, we just end up with this. Okay, now we come up with the magnetic equivalent of a description of how much energy is stored in the magnetic field while the current is flowing in this inductor. That's the next portion of the process. That then begins like this. What is delivered to the solenoid? What is delivered to the solenoid, P, is going to equal to epsilon times I, where this guy right here is the counter EMF. Now the counter EMF from earlier is equal to this expression here. Okay, we'll ignore the negative sign when I integrate and so forth in just a few moments. We'll ignore the negative sign. The negative sign is just indicating the direction of the red counter EMF on the top board. This right here is how much energy per second we're delivering to the solenoid while the current is flowing. In order to get a description, however, of energy as opposed to power, we basically have to take this and multiply it by time. So the infinitesimal amount of now magnetic energy that is stored within the inductor is equal to this guy multiplied by dt. It's equal to p dt. It's equal to this. So, and now what we'll do is then integrate over time to get a description of the amount of energy, potential energy, that is stored within the inductor. What we do, ignoring the negative sign, is not important at this point. Take this guy, just plug it into there, like this. Cancel out. This. What happens to that? Okay, the negative sign at this point is unimportant to describe potential energy. The negative sign just indicates the direction up on the top board. Just not important for this calculation. Okay? Now I get this. And now we integrate. So we get the total amount of energy stored in the B field now. We integrate that over current. This. So, and when you integrate this, you end up with something simple. This right here is the magnetic equivalent of electric potential energy as being 1/2 Q squared C. Like so, when talking about energy stored in the capacitor. So that's the energy stored in an inductor. Think of it this way. This is how you got to keep this straight in your head. You first of all switch on the battery, as I did up on the top board, the counter EMF builds up. Eventually you end up with a steady state current with a magnetic field through the solenoid. However, if you turn off the battery, a counter EMF builds up again to oppose that. So where did the energy of that counter EMF come up to try to stop the current? Well, it comes from the amount of energy that is stored as in the magnetic field in the inductor itself. So it's kind of like discharging a capacitor. It's like you charge the capacitor up, remove the battery, discharge the capacitor through a wire. That's relatively straightforward. This is the magnetic equivalent. Just like you charge the inductor up, you get a current flowing through it, there's a magnetic field, and then you discharge it through something else. So as the current starts to slow down, a counter EMF appears to oppose that. That battery appears. Where did the energy of that battery come from? It came from that. So that's the energy stored. And then we come up with energy density, just like we did for a capacitor. I know it's been a while, but does anybody remember what the energy density was? Energy per unit volume that is stored in the electric field? A little u sub E. It was a 1/2 times epsilon naught times E squared. Very good. It was this guy right here. What's the magnetic equivalent? Yeah, we did it. Chapter 24. Yeah, we did it. Yeah, that was the little u. That was energy per unit volume. What's the magnetic equivalent? Close. Close. It's not. It's not 1/2 mu naught b squared, but you're very close. It's the following. So he has length L. Length L. He has area A. And L is mu naught n squared A over L. So what I basically have to do is I have to take potential energy, 1/2 Li squared, and I have to divide that per unit volume to get energy density. Okay. Density of little u sub b is capital U sub b over volume, A times L. So I've got to take this and divide it by A times L. So 1/2 Li squared. 1/2 L. I squared over A times L. So this. Now, from earlier, B mu naught n I. Mu naught n I. Notice that that kind of appears right here. So how do I go to the B? This is kind of a little wonky. How do I want to do this? I think what I'm going to do is I'm going to take this and I'm going to solve it for I. Stick it here. That's probably the easiest way to do it. So I'm going to take this guy up here and these guys down there. I'm going to do that. I'm going to take it and square each of the terms. So you get kind of this. This junk.
What is it for?
I squared. Over A times L. Okay, now you just got to cancel out a bunch of crap. So let's see what happens with all the crap. N squared, goodbye. A, goodbye. L, goodbye. U naught, goodbye. What the hell is left? This. And so So you're not quite right. It's not 1/2 mu naught p squared. It's 1/2 over mu naught p squared. That's the energy per unit volume that's stored in the magnetic field. Once again, this is all just the magnetic equivalent of capacitance. Capacitance is relatively straightforward. Charge up plate, create an electric field, store energy, discharge it. In this case, you send a current through a coiled wire, build up a magnetic field when you do, store energy in the magnetic field, switch it over and discharge it into something else, and then that energy discharges through to something else. That's how I keep it straight in my head. It's the magnetic equivalent of capacitance. This is called inductance. So you can store energy in a magnetic field. That's not all that surprising, because we've already described how you store energy in a gravity field and how you store energy in an electric field. Is this tough? Yeah, but I know you guys are smart. I'm relying on your intellect to be able to get it. Okay, now this is kind of like the basic self-inductance problem. You do need to know this problem. Go through it yourselves. Go through this calculation here and see exactly what it is that I did. It probably won't appear on the test. Frankly, I'd be surprised if it did, but I have seen it happen once in a blue moon. The only other self-inductance situation that we need to know is the coax cable. This is the solenoid and the coax. When we did capacitance calculations, the basic one, of course, was the parallel plate. But does anybody remember the other capacitors that we briefly looked at? There was the cylindrical, the spherical, the isolated conductor. There's kind of like one more self-inductance that we need to know, and that's the coax. So we'll finish today with the coax. No, it doesn't sound like it, but believe me, a year or two from now, you'll look back on this. Oh, God, it was so easy. And I'm not saying that in the context of just physics. I'm saying that in the context of anything, regardless of what it is that you're going to go on and study. A couple of years from now, when you gain so much more experience, you're going to look back on what is now, yes, in high school, very difficult material. You're going to look at it like this. It happens, believe me. It may not seem like it, Ariana, but it does here, regardless of what you study. You're going to go on into biochemistry, you're going to go on into physics, you're going to go on into engineering, you're going to go on into CS, you're going to go on into law, you're going to go on into business. All of the gory details of whatever it is that you're going to study, when you look back on these days here, you're like, my God, that was so simple.
Truck driving school.
Maybe not truck driving school. Driving a truck, by the way, is really hard. Anybody here ever tried driving a large vehicle? It's not easy.
Thank you for appreciating my job.
I drove a semi once, about 10 miles, nearly ruined. A friend of mine. A friend of mine actually was a truck driver. No, it's not a boss. All right, the only other inductance problem that we have to look at, self-inductance, is the coax. So here's how
Jordan, but how else am I going to pick you up? There's so much.
And once again, let's see, it's been a while since I've done this. All right, so here's our coax situation, where we have a thin cylindrical shell here, radius A, thin cylindrical shell here, radius B. Remember, this is all vacuum. Like so. Now, there's no magnetic field in here. There's no ion closed. There's no magnetic field out here. The total ion closed is equal to 0. The only place that we do have a magnetic field is in here. Remember from Ampere's law, it basically circulates like so. Here's our magnetic field, like so. B circulating in this manner, like the direction's correct here. Circulates like this, like so. So then therefore, I am going to have a flux that has to be looked at in cross-section, if I remember. Yeah, it has to be looked at in cross-section. Okay, so first of all, the B field itself. The B field is mu naught I over 2pi r. And this right here is our radius r. Okay, now what I'm going to do, if I remember to do this right, I have to take the coax and I have to look at it in cross-section. I have to look at it like this. So here's the coax in cross-section. Let's cross this section. So what the hell is what here? Okay, well, this distance here is small a. This distance here is small b. Okay, now let's picture a little box here. Like so. That little box there has an infinitesimal area associated with it. Yeah. Okay, right here is an infinitesimal length in the radial direction from the top board. That's a dr. Right here is an infinitesimal length in this direction along the axis of the coax. It's called dx. So, okay, now let's see how I've circulated this. The current right here is pointing in this direction like so. Okay, now passing through the box right here is the B field going into the page like so, and then it comes out of another box down here, coming out of the page like so. So this is the inner conductor right here, and the current is flowing to the left on my diagram. The B field circulates around like so. So right here is our B field. And it's okay, now what I have to do is calculate the flux through that little red box, and that will give me an infinitesimal value like so. Also, it's going to be this. It's going to be a BdA, and then I am going to have the integrated in this case. Okay, now the area. dA is just a little rectangle. So it's like a dr times dx. Think about it. Okay, now the B is mu naught I over 2pi r. So, and now to get the total flux, I have to integrate that.
Is the BD something you've calculated before?
Yes, that was Ampere's law back in early in chapter 28 for cones. Okay, so now phi. Integral to the end. Somewhere. There we go. So, yeah, I figured out this one. Yeah, is there a double root on there? It's easy to double. Okay, so inner integral over R. We're integrating from A to B. Outer integral. We're integrating over length. 0 to L. So, okay, integral 0 to L dx. What is that? L. Okay, integral of 1 over R dr. Natural log. Natural log of B minus A. So I have to use the integral. Okay, now this is the bulk of the calculation to find the self-inductance. The last step is really just one step. Flux equals self-inductance times current. The N is equal to 1 for the coax. It's not a bunch of winding, it's just one wire, that's all. So the N is just equal to 1. So flux equals self-inductance times R. So take that guy, just stick it there. So So I cancel out. Notice how the problem is phrased out there. Self-inductance per unit length, just like the cylindrical capacitor. Capacitance per unit length. This is the magnetic equivalent. So self-inductance per unit length. Geometry. Frankly, I'd be surprised if this was on the exam, but this is then how we find the self-inductance. It's the one double flux and then one here. After this, next time in class, we have 1, 2, 3 circuits to examine, and then fourth, we then wrap everything up with a brief statement involving overall Maxwell's equations. So almost to the finish line. Stay with me. We'll finish. We will get to the finish line probably less than halfway through of the next class period. Tomorrow, another assigned for chapter 28 is due as it always is on the 1st. Monday of next week, as I said, we finish the curriculum. Whatever time there is left to review, we will do so. I have a very detailed study guide of both the first and the second semester to give you. I'll give you that on Monday. And then Wednesday is the magnetism exam. As always, it is open note. An open book. It's the last open note exam. And then Friday of next week is the final exam for both mechanics and electricity and magnetism. Multiple choice, each multiple choice test is 35 points. There are 2 of them. It will take the full 100 minutes. You're allowed 45 minutes per test. So that's a total of 90 minutes, with a small 2-minute break or so in between. That's then on Friday of next week. When is the actual AP exam itself? The following Monday. It is always the second Monday of the AP exam schedule. It's Monday the 9th. What do we do after the AP exam? We'll wait until then.
Just